In this section, we will discuss transmit diversity schemes that are used in MIMO OFDM systems. For example, in 802.11n, there are two diversity schemes that are used for transmit diversity. One is the space-time block coding and the lamouti scheme, and also cyclic delay diversity. We will cover both the lamouti scheme and the cyclic delay diversity scheme, or CDD scheme. The idea behind transmit diversity is that when you have multiple transmit chains, how can we exploit the fact that we have these multiple transmit chains in order to achieve diversity at the receiver? And in many cases, you have receivers with one antenna, like in cellular or ultramobile, in which case it is beneficial to place the diversity at the transmit side and simplify the receiver by only having one receive chain. However, you can have diversity with both transmit diversity and receive diversity, as we will explain. For example, with CDD, you can have transmit diversity with CDD, and at the receive side you can achieve receive diversity with multiple receive chains using maximal ratio combining, or MRC. And of course, MIMO itself, when you implement a MIMO equalizer, it will combine, of course, the diversity both of the transmit side and the receive side in an elegant fashion to provide either spatial multiplexing or, where appropriate, as we have seen, diversity. For example, in the case of beam forming. However, in this section, we are going to talk about transmit diversity, limit our discussion to transmit diversity, and have a single antenna at the receiver. Again, you can have multiple antennas at the receiver and extend these techniques. One of the best known schemes for transmit diversity is the lamouti scheme, which was discovered by Siavash Lamouti. In a famous paper shown over here, we give the reference. The lamouti scheme works as follows. We have a spatial stream, and consider the symbols S0, S1, S2. Consider the fact that each symbol is delayed by a time t. And also, since we're dealing with MIMO OFDM or OFDM in general, consider the fact that S0 is an OFDM symbol and S1 is the next OFDM symbol, and therefore t, in the case of, for example, 802.11a, would be 4 microseconds. Also consider the fact that in OFDM we're dealing with multiple carriers, and then consider the fact that S0 is a carrier within the OFDM symbol at this time, and S1 is a carrier within the OFDM symbol delayed by t or 4 microseconds. So we can be dealing with carriers that are delayed in time by 4 microseconds, and each carrier that goes through the channel can then be treated as exhibiting flat fading in OFDM. So that's a key point to remember in the derivation of the lamouti scheme. So consider S0 and S1 to be carriers within the OFDM symbols, and they are delayed by t seconds, which in our case is 4 microseconds for a example OFDM system based on 802.11a. Now, if we were going to add the lamouti scheme for transmit diversity to 802.11a, we would have to break the standard, as we shall show, in terms of the detection at the receiver side. But as we discussed with a cyclic delay diversity, we can actually add transmit diversity in 802.11a without breaking the receiver. So the lamouti scheme basically takes the carrier S0 and S1 and maps S0 at time 0 to the transmit antenna 0, and maps S1 to transmit antenna number 1, and in the next time cycle, since it's delaying S0 and S1, it'll take S1 conjugate, and then at the next time slot will transmit minus S1 conjugate from transmitter 0 and S1 conjugate from transmit 1. So if we look at these time slots, at first we're transmitting S0, S1, then we're transmitting minus S1 conjugate and S0 conjugate on antenna number 1. Then we start processing the next two symbols, S2 and S3, which are arranged in the similar fashion. Let's take a good look at this diagram over. We see that from transmit antenna number 0 and transmit antenna number 1, we have S0 transmitted from transmit antenna 0, and at the same time S1 is transmitted, transmit antenna number 1. Then we transmit minus S1 conjugate from antenna 0, and then S0 conjugate from transmit antenna number 1. S0 goes through the channel and is received by the receive antenna. So as S0 goes through the channel, again we're talking about a carrier, so it exhibits flat fading. And S1 also goes through the channel. They're combined at the receiver. We go through a detection algorithm that we will discuss and recover the original sequence S0, S1. We will discuss this detection mechanism, which gives us the great performance of the lamouti scheme. If we look at here, we see that S0 goes through the channel and exhibits flat fading. It gets multiplied by a complex number h sub 0 with a magnitude and phase. Since this transmit antenna number 1 goes through a different multipath to the receiver, it exhibits a different flat fading, a different complex multiplication by h1, again with a magnitude and phase. They're combined at the receiver. Now, at the receiver, we receive RT, which is the received signal, plus noise, of course, and we delay it, and we also have the delayed signal RT plus T. Then what we do is we, in the detection process, in order to obtain estimates of the transmitted symbols, we perform this operation. We form a matrix H0 conjugate H1, H1 conjugate minus H0, so a 2x2 matrix based on the channel frequency responses at the carrier frequencies. This 2x2 matrix is then multiplied by the received signal and the delayed conjugate signal, and we recover the estimates of the transmitted symbols plus noise, which we can then pass through a maximum likelihood detector and detect the actual transmitted symbols. Next, we're going to go into the mathematics and show why this works. But before we go to the next step, it is very important to understand that in the lamouti scheme, we assume that the receiver has knowledge of the channel. So the receiver has knowledge of H0 and H1. So we assume there is a training sequence that is used to then obtain the channel responses H0 and H1 per carrier. This is very important. So let's take a look at the math. First of all, H0 of t we're going to assume is equal to H0 of t plus capital T. That is, that the channel does not change within a time frame of t seconds. So if the channel does not change within the time frame of t seconds, then H0 of t and H0 of t plus t is equal to H0 complex number with a magnitude alpha 0 and a phase theta sub 0. The same holds true for the second branch from the transmit antenna 1 to the receive antenna. And we have a complex number H1 which doesn't change during that period of t seconds. Given these assumptions, then R0 of t is equal to H0 S0 plus H1 S1 plus the noise S0. Let's take a look at that. So we go back to this situation here at this time slot here, the received signal is equal to S0 times H0 plus S1 times H1. They're added at the receiver plus noise and the received chain. So that's this expression over here. At the next time slot, we have a delay of t seconds. Then let's go back to this picture. At this time slot, then we get the received signal is equal to minus S1 conjugate H0 plus S0 conjugate times H1 plus the noise. So that's this expression over here. So now we have the expressions for R0 of t and R1 of t, and R1 of t is R of t delayed by t seconds. So this corresponds to R0 of t, and this corresponds to R1 of t. Now we form the estimates S0 tilde and S1 tilde as follows. S0 tilde is a combination of R0 times H0 conjugate plus the next time slot H1 conjugate times H1, and we also form S1 tilde, which is equal to H1 conjugate R0 minus H0 R1 conjugate. And this is just this matrix operation on R0 and R1 conjugate. If we then form this expression and calculate S0 tilde and S1 tilde, then if we substitute for R0 and R1 according to these two expressions here, and combine terms and simplify, we get that S0 tilde is equal to alpha 0 squared plus alpha 1 squared times S0 plus terms associated with the noise in the receive path and the channel. S1 is also equal to alpha 0 squared plus alpha 1 squared times S1. Now, if we look at this expression here, let's assume for the moment that we have a very high signal to noise ratio and that we can ignore the noise terms. And this is just a temporary assumption here. Then if we ignore the noise terms, then we get that S0 tilde is just equal to some proportionality constant times S0, and S1 is equal to the same constant times S1. So we have recovered the originally transmitted carriers using the lamouti scheme. Now let's take a look at these terms alpha 0 and alpha 1, which correspond to the different paths from the transmit antenna 0 to the receive antenna and transmit antenna number 1 to the receive antenna. It turns out that diversity is gained by the fact that if alpha 0 happens to be a deep fade, then alpha 1 is not necessarily at a deep fade, and the signal is still recovered. Similarly, if alpha 1 is at a deep fade, but alpha 0 is not at a deep fade, we can still recover the signal. And if both of them happen to be either strong or even if both are weak, we're still combining both in order to achieve diversity, and we will have a diversity gain. Again, looking at the two separate paths and considering the fact that the transmit antennas will normally be spaced half a wavelength apart, as we've shown earlier, there's a good chance that if one path exhibits a deep fade, the other path is at a peak or vice versa, or somewhere in between, and here you can see how we get the diversity gain. The other important observation is the fact that the noise terms are related to the matrix composed of elements of the channel matrix H0 and H1, and we do not have noise enhancement in the case of the lamouti scheme, unlike the zero forcing MIMO equalizer. So let's go ahead and take a look at the performance of the lamouti scheme versus spatial multiplexing using zero forcing as the equalizer for MIMO system, and also using a maximum likelihood MIMO equalizer. These results are from a great paper by Shafi and company on the theory to practice an overview of MIMO spacetime codes and wireless systems back in 2003. The plots are the bit error rate versus the signal to noise ratio per receive antenna. And also note that STBC stands for space-time block coding. And the family of curves over here, let's start out with the top curve. That corresponds to spatial multiplexing using zero forcing, and this is a 2x2 system. So in the case of the top curve, we're using the MIMO 2x2 MIMO system with zero forcing equalizer, which we have discussed, and we see its performance, the bit error rate versus the signal noise ratio per receive antenna. Now obviously, as the signal to noise ratio increases, the bit error rate decreases, but not very rapidly in the case of the zero forcing MIMO equalizer. So each stream is using a 4 QAM, so that the overall throughput is the combination of the 4 QAM streams. So we're using two spatial streams. Let's take a look at this curve over here. This is for the spatial multiplexing using maximum likelihood, again with 4 QAM. We see that the maximum likelihood decoder for 2x2 MIMO greatly outperforms the zero forcing MIMO equalizer. And the fact is that as we increase the signal noise ratio, we get a steep decline in the bit error rate. Now, this is very important. If we take a look at the lamouti scheme, which is a solid curve over here, the lamouti scheme is using 16 QAM because the lamouti scheme is not using spatial multiplexing but transmit diversity with one spatial stream. But since we get a diversity gain, we have a higher signal to noise ratio, so we can actually transmit a 16 QAM signal through the system. So the actual throughput of the lamouti scheme with 16 QAM is equal to the 2x2 MIMO maximum likelihood system with 2 spatial streams each at 4 QAM. So the bit rates are the same, yet we see that the lamouti scheme has a much better performance than the spatially multiplexing 2x2 MIMO system using maximum likelihood. We will present many other plots, and we have previously presented plots that show that the lamouti scheme achieves a great performance over SISO systems and also in many cases open loop MIMO systems depending on the conditions. And here we clearly show that it has an advantage over even a 2x2 maximum likelihood MIMO open loop system. In this section we will present the cyclic delay diversity scheme for transmit diversity. CDD has a great advantage in the sense that an existing 802.11a system can employ CDD transmit diversity without breaking the legacy 802.11a receiver. And we'll discuss why that's the case. So that's why CDD is very important. Over here we show the general block diagram of a transmit diversity scheme with one receive antenna. So the idea is that we're using an OFDM system, and how can we incorporate a transmit diversity scheme in order to exploit the fact that we have multiple transmit antennas and transmit chains. For example, as we've discussed in MIMO systems, we have multiple output, multiple input, multiple transmit chains, multiple receive chains, and usually prior to using MIMO, we need to train the receiver in order to obtain an estimate of the channel. We also have to do, prior to that, acquisition and packet detection. And in 802.11n, the system can use the same acquisition that is used in 802.11a in order to be compatible with legacy systems. And at the same time, we need to use multiple transmit chains, so we're not going to shut off the extra transmit chains during the initial acquisition. It will be desirable to actually transmit the packet preamble over all transmit antennas and exploit the fact that we can achieve transmit diversity without breaking the legacy packet detection scheme of 802.11a, and that's what CDD brings to the table, and that's why it is used in 802.11n draft standard. A great reference for CDD is Demant's paper et al. Beam forming in combination with space-time diversity for broadband OFDM systems. And here we have a nice diagram that they have. Basically we're showing two OFDM symbols, one in green and one in red. In the case of OFDM we have the cyclic prefix, which in the case of 802.11a is 800 nanoseconds, or a copy of 16 samples at 20 megahertz of the OFDM symbol that is then prefixed to the OFDM symbol, forming a 4 microsecond symbol. The OFDM symbol itself is 3.2 microseconds, and the cyclic prefix is 800 nanoseconds, or 0.8 microseconds, for the overall length of the OFDM symbol is 4 microseconds. So here we see that the cyclic prefix is an exact copy of this part of the OFDM symbol that is then prefixed to the OFDM symbol, forming the overall OFDM symbol of 4 microseconds with cyclic prefix. Here we're showing one harmonic in the OFDM symbol, and notice that in an OFDM symbol the signal is continuous across the cyclic prefix into the OFDM symbol, and that has a lot to do with the way that an FFT can be formulated from a Fourier series. But we won't get into that, but it's very important to note that this is continuous. Now we're going to ignore delay diversity and go straight to cyclic delay diversity, because the fact that an OFDM symbol is generated as the output of the inverse FFT and is cyclic in nature, then we're going to exploit that. In this case, compare the reference signal above to the cyclically delayed signal shown over here. In this case we have a cyclic delay of delta, and if we compare these two, we see that we're actually shifting the OFDM symbol cyclically through the cyclic prefix. So if you take a look at this signal here, and as we move it across, we delay it, we're actually cyclically moving in to the cyclic prefix and also moving that forward, and we get this signal here. So that's a cyclic shift, cyclic delay of the original reference signal. Now here we're showing also the fact that in the cyclic, at the receiver, the cyclic prefix has intersymbol interference from the previous symbol, but what we need to be concerned with is the fact that due to the cyclic nature of the inverse FFT, a cyclic delay is equivalent to a delay in the frequency domain, so that at the receiver, adding a cyclic delay is equivalent to a fixed delay in the frequency response, and therefore during the synchronization and acquisition, the effect of the cyclic delay would be incorporated into the channel frequency response estimation process, and the equalizer would take care of it. This is a very important point. So let's take a look at this diagram over here. So the way CDD works is we have a OFDM modulator. Consider that at this point we're at the output of the inverse FFT, and we have the 3.2 microsecond OFDM symbols with the 52 carriers and the null at DC and the nulls at the guard interval. And this is prior to adding the cyclic prefix. So what we do is, for the first transmit chain, we don't introduce any cyclic delay. For the second transmit branch, we introduce a cyclic delay, here shown as delta cyclic 1. And remember that the cyclic delay on the OFDM symbol then translates into the guard interval. So what we do is we actually do a cyclic shift within the OFDM symbol and then attach the cyclic prefix. And for N transmit antennas, we add different cyclic delays for each different transmit chain. Now let's take the case where we're considering cyclic delay with two chains. Now, as the signal is transmitted through the channel, it is received by the receiver through different multipaths. Now, if we did not add the cyclic delay in the OFDM symbol, and we transmitted the symbol through the two transmit chains, then there's a high likelihood that at the receiver the signal would exhibit constructive and destructive combination. And this is especially detrimental during the transmission of the fixed preamble, which happens to be the same signal that is transmitted from both transmit antennas. So during the preamble processing, we will exhibit constructive and destructive combination, and the signal will vary. We'd have a large peak to average ratio, and we can have some deep fades. However, by adding the cyclic delay, then these two signals become somewhat decorrelated when they are added in the receive antenna, and this improves the performance and also adds a diversity gain. And notice that the fact that the signal from this transmit antenna is delayed compared to the first transmit antenna and goes through the channel when it is combined at the receiver is just like a delayed multipath, and the equalizer in the OFDM receiver will estimate and eliminate that distortion. And this is a key point in the power of a CDD transmit diversity scheme. In particular, a legacy 802.11a system using a single antenna, for example, does not break by introducing transmit diversity using CDD. This is very important. This is one of the big reasons why CDD was adapted by the 802.11n draft, because it provides transmit diversity. We have the fact that all transmit antennas are active. It improves the range by adding diversity during the processing of the preamble, and does not break the legacy 802.11a systems that may coexist with the 11n system. And of course, as we'll point out later, once the preamble is processed and the signal field has been detected, then the legacy systems will be spoofed into not transmitting during the processing that is required for the 11N MIMO packets. So we'll get into that much later. So basically we've shown that cyclic delay diversity is a scheme in which by introducing a cyclic shift in the OFDM symbol we can achieve transmit diversity using multiple transmit streams, and it does not break the legacy system in the sense that the multiple paths from the transmitters to the receiver and the fact that the multipaths have a cyclic delay can be modeled into the channel and are equalized by the receiver, so we don't have to change the architecture of the receiver in order to support cyclic delay diversity. Here's a table from the 11N draft, and let's spend some time on it. First of all, we're showing the number of TX chains. If the number of TX chains is equal to 1, then the cyclic shift for the first transmit chain is 0 nanoseconds, and of course we don't have any other chains. When we add another chain for example, a 2x2 system, the number of transmit chains is equal to 2. In the first chain we have 0 cyclic delay, 0 nanoseconds. In the second transmit chain, we add a minus 200 nanosecond cyclic shift to the second transmit chain. So in this case, the cyclic delay here is minus 200 nanoseconds. If we have 3 chains, then we take the delay, the cyclic delay, and divide it, so we have now 0 nanoseconds and minus 100 nanoseconds and minus 200 nanoseconds. If we have 4 chains, then we have 0 nanoseconds, minus 50 nanoseconds, minus 100 nanoseconds, and minus 150 nanoseconds, so that the cyclic delays between each branch is 50 nanoseconds. So it's a fixed amount. In this case, it's minus 200 nanoseconds. In this case, it's minus 100 nanoseconds between each transmit branch. And of course, we can't exceed a large number here because we are processing the legacy preamp. Now, it turns out that CDD can be used effectively for the whole packet in legacy 802.11a systems. So, even in an 11N system with CDD, we can operate legacy systems with better performance and greater range, exploiting CDD even with the legacy packets. Now, as we'll point out in 11N, CDD is used during the processing of the legacy preamble, but is not used when we send the data portion of the packet using MIMO, after, of course, training for the H matrix and performing the MIMO equalizer on the data part of the packet. In that case, we do not use CDD. CDD is used in the legacy preamble. Finally, we should point out that the performance of CDD is not anywhere close to the lamouti scheme. The lamouti scheme has a much greater diversity gain than the cyclic delay scheme. However, CDD is absolutely required in order to add transmit diversity during the processing of the legacy preamble or legacy packets in 802.11n.